Our speaker today is Professor Edward Witten from the Institute for Advanced Study, and he will be talking on strong coupling dynamics of string theory.
Thank you. Is this on? Yeah. Well, as many of you know, in the last 15 years or so, there's been a lot of interest in theories of quantum gravity and particle physics derived from string theory. And one of the main attractions, of course, is that via string theory you get consistent theories that include gravity in quantum mechanics. And another motivation is that qualitatively particle physics comes out very nicely. But one of the motivations always was, one of the attractions has always been the high degree of uniqueness. In field theory, you can take any set of elementary fields you want and write down any Lagrangian you want. But in string theory, the rules are much tighter, and there are just a few of them. But there used to be something a little bit embarrassing. 10 years ago, you'd give a seminar on this, and you'd say, there's this fantastic structure, and it has a high degree of uniqueness, and there are 5 of them. Well, what I'm going to try to convince you today is that there's really only one string theory. That all these fantastic things, all these 5 theories, are really different manifestations of the same thing. And for interest, we also get 11-dimensional supergravity as part of the same story. So all these fancy theories that have fascinated theoretical physicists so much are really different manifestations of the same thing that we really don't understand. Well, we're going to learn all this. See, we can't learn all this for weak coupling, because for weak coupling it doesn't appear to be true. We're going to learn all this. The mic is working, isn't it? Yeah. We're going to learn all this by going to strong coupling, by finding out what happens when the coupling is strong, and then learning new lessons which will ultimately enable us to conclude, among other things, that apparently there's only one big string theory up there. But we'll start simply with the project of determining how the different string theories behave in different numbers of dimensions. So that means, most simply, we take a 10-dimensional world, which is our d-dimensional Minkowski space times a torus. We take the string coupling constant to infinity. So roughly speaking, we take Newton's constant to infinity, keeping fixed the radius of the torus. And we ask, what happens? Well, that's the kind of question you're supposed to not be able to answer. You're supposed to not be able to say what happens for strong coupling. You can't say it for QCD except by numerical simulations. And normally in physics, you can't say what happens for strong coupling. But in the last couple of years, one has learned in supersymmetric field theory, I explained a little bit of this yesterday in the math department, that often in supersymmetric field theory, you can learn what happens for strong coupling. And here we'll see that apparently in string theory, you can determine what happens for strong coupling. Now, the reason you can, the reason you can determine what happens for strong coupling is that when you try to determine it, you get what looks like a hopeless mess. And you get into apparent paradoxes, and when you find the right interpretation, various things snap into place. So we'll begin by considering the so-called type 2A superstring theory in 10 dimensions. The bosonic field are the metric tensor, a scalar usually called the dilaton, and a 2-form or antisymmetric tensor field B. Those come from the Nevers-Schwarz sector, and from the Ramon sector, there's also a U1 gauge field A, and there's a 3-form A sub 3. And we could write down the low energy effective action, which is just one of the 10-dimensional supergravity theories. And then, well, Newton's constant is this factor in front essentially, but the string coupling constant is usually called e to the phi. But there's a peculiarity, which is that the usual Newton's constant factor multiplies part of the action, but it doesn't multiply the fields that come from the Ramon sector. Well, since the theory has a U1 gauge field A, you can imagine particles that are electrically charged coupling to this U1 field. You can imagine them, but they're absent in the elementary string spectrum. But although they're not present in the elementary string spectrum, perhaps they're present non-perturbatively. Well, if such charges exist, then this electric charge appears as a central term in the supersymmetry algebra. And you can use the supersymmetry algebra to prove an inequality that a particle of mass of charge W has a mass which is at least the absolute value of W divided by lambda, where lambda is the string coupling constant, the square root of Newton's constant. Now, particles for which this inequality is saturated play a special role. They are in so-called small multiplets of supersymmetry. And because the multiplets are small, it's like representations of ordinary groups that depend on some parameters, but for certain values of the parameters, you can construct smaller unitary representations than for generic values of the parameters. The particles with the lowest possible mass form smaller representations of supersymmetry, and the representations being small is a condition that's stable under perturbations. So if there are particles with this magic mass, then their existence should be independent of the coupling. Well, in recent work, Hall and Townsend pointed out that below 10 dimensions, such states must exist because of some of the new stringy duality symmetries that I'll be reminding you a little bit about later on, and proposed that these states originate as extreme black holes. In other words, the idea is that in any dimension, a black hole of charge W has a mass which is given at least by gm squared equals W squared. M is the mass and G is Newton's constant. This is, in any dimension, I've suppressed a constant that involves a power of pi that depends on the dimension. But there's such an inequality in any dimension between the mass of a black hole and its charge. And with Newton's constant being the square of the string coupling constant, the mass inequality for black holes is the same as was the mass inequality that we got from the supersymmetry algebra. And that's no coincidence. It's related to the fact that extreme black holes are invariant under some supersymmetries and correspond upon quantization to these small multiplets.
So extreme means?
Extreme black holes means black holes with the smallest mass for given charge. If you look up in four-dimensional general relativity, you'll find general relativity books usually deduce this in 4 dimensions, but there's a similar formula in any dimension. For a given electric charge, there's the smallest mass that you can have for a black hole. Otherwise, you get a naked singularity instead of a black hole. And you see, if you fix the electric charge, a black hole will presumably radiate by the Hawking effect and lower its mass, and presumably it will keep lowering its mass until it reaches this magic value, the lowest one which is allowed. And that coincides with the lowest one allowed by the supersymmetric inequality. And they coincide because the extreme black hole is invariant under some supersymmetries. That was shown 10 or 15 years ago by, I think, Hall and Gibbons. Well, see, the stringy dualities, which I'll remind you about in a bit, seem to require that these states exist below 10 dimensions. But if so, they really have to exist in 10 dimensions. Because if in 10 dimensions the mass of the lightest charged state was bounded above that limiting value by some constant, then the same would be true after compactification on a sufficiently big circle. So they can't really exist below 10 dimensions unless they exist in 10 dimensions. Well, apart from everything else I'm going to tell you, the existence of these states has an interesting consequence, which is that you see, these would be particles with masses of order 1 over lambda, in contrast to solitons, which have masses of order 1 over lambda squared. Now, usual non-perturbative effects in physics go as e to the minus 1 over lambda squared. And you can think of that intuitively as the contribution of a soliton loop. So if you have particles with this kind of mass, you should get non-perturbative effects of this order. So on this grounds, we conclude that at least this string theory has non-perturbative effects bigger than the usual non-perturbative effects seen in most physical theories. That's been conjectured previously from matrix models and analogy with QCD in the 1 over n expansion by Schenker. Well, what values of the charge exist? Well, we'd like to assume that the charge is quantized, either because the alternative seems pathological, or anyway, charge quantization is required by these dualities. If it's quantized, what values of the quantum charge occur? Well, classically, the extreme black hole can have any charge. So the quantum version of a classical thing having any charge is that it has any charge allowed by the quantization. So we think there's some quantum of charge that we haven't determined. Actually, it was determined in a recent paper by Strominger and Jeff Harvey. But anyway, there's some quantum of charge, and these black holes have a charge which is any integer times W naught. So for every integer n, we expect a supermultiplet whose spins go up to 2. They have to go at least up to 2 because in this kind of supergravity in 10 dimensions, there's no multiplet smaller than that. If they weren't in little multiplets, the spins would go up to 4. With little multiplets, we can keep the spins bounded by 2. So for every integer n, we think we have a supermultiplet with spins going up to 2 with this kind of mass. And we've been perhaps thinking for weak coupling. But because they're in small multiplets, their existence and their mass, their existence is independent of the coupling, and their mass is given exactly by this formula. So let's simply have the daring to follow that formula into strong coupling. Well, do we indeed dare? Well, of course we might dare simply because there's the supersymmetric argument that the formula is exact. But the other reason we ought to dare, I think, is that similar daring has now, in the last few years, been extremely successful at illuminating the dynamics of supersymmetric gauge theories in 4 dimensions. I mean, there are more tricks, but one of the most basic tricks is just having the daring to follow such formulas into strong coupling. And now, many things that were totally beyond reach analytically in 4-dimensional gauge theories are now under control, at least in the supersymmetric case, through daring such as this, with the result that now in 4 dimensions we have quantitative models exhibiting quark confinement, chiral symmetry breaking, confinement with and without chiral symmetry breaking with and without confinement, composite massless fermions with and without chiral symmetry breaking, and so on. So one of the things that led to what I think is a real reinvigoration of our whole understanding of 4-dimensional field theory is the daring to follow formulas such as this one, even into strong coupling. So let's apply that same daring in string theory. Well, for strong coupling, these particles go to 0 mass because of the lambda in the denominator, and now we are in serious trouble because we've got infinitely many light particles. That already can hardly be a local field theory. But even worse, we've got light particles of spin 2, and they're electrically charged to boot. So what kind of sensible theory can have light electrical charges in 10 dimensions? Well, it can't be any kind of 10-dimensional local field theory. But there's a very simple way to get such a spectrum. The spectrum looks very much like what you get if you take an 11-dimensional theory on R10 times a circle and dimensionally reduce it. In other words, you expand in harmonics on the circle so that one field in 11 dimensions becomes infinitely many fields in 10 dimensions. And then the electrical charge in 10 dimensions is just the eigenvalue under rotations of the circle. And there are infinitely many, and there's a multiplet for every charge. because the functions on the circle have one harmonic e to the im theta for every m. Moreover, there's an 11-dimensional theory with just the right properties, namely 11-dimensional supergravity. So I make my proposal that the strong coupling limit of type 2a superstrings in 10 dimensions is 11-dimensional supergravity on R10 times a circle. Well, how can we get some evidence to support that view? Well, there's a very preliminary test we ought to make. You see, we can take 11-dimensional supergravity. It doesn't have any parameters except Newton's constant, which I said I'm working in units where that's 1, where the 11-dimensional Newton constant is 1. And we can formulate it on R10 times a circle and give the circle a radius r. And then the effective 10-dimensional theory will have the same spectrum and the same supersymmetric invariance as type 2a superstrings. But when you match up the parameters more precisely, you find that the relation between the string coupling constant and the 11-dimensional radius is that the radius goes like lambda to the 2/3. This is a very fundamental formula that avoids a contradiction, because it shows that when the string coupling was weak, the radius was small. And of course, when the radius is small, for instance, for weak coupling, it's sub-Planckian, 11-dimensional supergravity isn't a sensible description. That's okay, because weakly coupled string theory doesn't look 11-dimensional. On the other hand, this theory doesn't look like string theory, but that's all right, because when the radius is big, the string coupling constant is big, or we don't know directly. This theory doesn't look like perturbative string theory, but perturbative string theory isn't valid because when the radius is big, because then lambda is big. To put it differently, the string description is good when lambda is small. Supergravity makes sense when r is much bigger than the Planck length, or in other words, big. And the formula shows that you can't directly compare the two descriptions. Each one is the strong coupling limit of the other. So at least we avoid an immediate contradiction. Moreover, the formula shows that if true, the description is useful. When the string coupling constant goes to infinity, the radius goes to infinity, and then the 11-dimensional supergravity is compactified on a length scale much above the Planck scale, at which supergravity is weakly coupled, and the 11-dimensional theory is a useful description, weakly coupled at its compactification scale. So the discussion at least makes sense, and if it's true, it gives an effective determination of the strong coupling behavior. That is, the strong coupling behavior of the string theory is weakly coupled in terms of the 11-dimensional supergravity. Well, can we give significant further evidence for this picture? And in particular, can we see signs of Lorentz invariance between the 11th dimension and the original 10? The most striking thing about this is the appearance, when we go to strong coupling, of an 11th dimension that comes out of thin air. And moreover, there should be perfect symmetry between the 11th dimension and the first 10, because 11-dimensional supergravity has that symmetry. Well, I claim we can find evidence for this using the duality symmetries that string theory is believed to possess below 10 dimensions. And here I'll be comparing especially to some of the ideas of Hull and Townsend. And by the way, some of what I've said so far also overlaps with remarks in a subsequent paper by Townsend. Well, the duality theories, symmetries of string theory, at least type 2 string theories, really come from another 10-dimensional phenomenon. If we took, I said at the beginning that 10 years ago we had the embarrassment that there were 5 consistent string theories plus a close cousin, which was 11-dimensional supergravity. I promised you that by the end of the talk we'll just have one big theory. So one of those other 5 theories was the type 2b theory in 10 dimensions. And as a classical theory it has SL2R symmetry. Hull and Townsend proposed that an SL2Z subgroup of this is a symmetry of the type 2B superstring theory. See, the motivation is in part that the symmetry of the string theory can't be a subgroup that's bigger than SL2Z. So this is the most optimistic possible assumption. And when you check the most optimistic possible assumption, it turns out that things work out. For instance, in the computation that I'll mention presently. Well, if this hypothesis is true, it determines what the type 2B theory does in 10 dimensions. Its strong coupling limit is the same as its weak coupling limit because of SL2Z. Completely different from what happened for type 2A. I proposed that the type 2A theory for strong coupling lands us in 11 dimensions, while the type 2B theory for strong coupling is just itself again. Well, they're completely different in 10 dimensions, but below 10, see, in winnowing the number of theories below 5, one bit of winnowing that was done some years ago by Stein-Seiberg and by Polchinski and Lee and Dye was that the 2A and 2B theories below 10 dimensions are equivalent by what's called T-Duality, a better understood symmetry of string theory, which is the statement that there's a minimum length because the radius r is equivalent to a radius alpha prime over r. Alpha prime is 10 to the minus 32 centimeters squared. So, in 10 dimensions, apparently these theories have a completely different strong coupling limit. But below 10 dimensions, they're equivalent. Now, if you compactify the type 2B theory below 10 dimensions, it gets a non-classical symmetry group that we know about. Non-classical means a symmetry group that field theory wouldn't have, but that the string theory has, and which we definitely know about. It's a generalization of R going to alpha prime over R. And in D dimensions, it's this discrete subgroup SO10 minus D, 10 minus D. An integral form of that group. This doesn't commute with SL2Z, and together they generate a bigger group, which is the U-duality group G. And this G is an integral version, as Hal and Townsend point out, of the strange non-compact symmetries that were discovered many years back for supergravities. Various of these supergravities in different dimensions have non-classical symmetries, for instance E7 in 4 dimensions. And in 4 dimensions, G would be E7. An example of this is that in D equals 4, G is just an integral form of E7. Another example, just for fun, is that in 7 dimensions, the T-duality group, which we know to be true, is SL4, and then the U-duality group turns out to be SL5. Well, in supergravity, one has these symmetries, but the non-compact symmetry is always broken down to its maximal compact subgroup. For instance, in this example, the maximal compact subgroup is SO5. And because of the symmetry breaking, the moduli space of vacua in the supergravity theory is the homogeneous space G mod K. The string theory has precisely the same moduli space of vacua because that structure is completely determined by the low energy supergravity. Well, the moduli space of vacua is G mod K locally, but globally we're claiming that an integral subgroup of G is a symmetry of the string theory. And you really should divide by that, because you can argue in string theory that all these discrete symmetries are really discrete gauge symmetries. So really the moduli space of vacua is a double coset space, where you divide by K on the right and by G of Z on the left. So that's the basic symmetry. There's this integral G of Z symmetry. And what are the physical degrees of freedom? Well, among other things, you have massless U1 gauge bosons, and they transform in a representation of G. For instance, in 7 dimensions, which I'm giving as an illustration, G is SL5, and the representation is the antisymmetric tensor, which is 10-dimensional. There are therefore 10 gauge charges, and just as in 10 dimensions where there was one such charge, here there are 10 of them. They appear as central charges in the supersymmetry algebra. And then we get, once again, a mass formula that the mass of any particle is bounded below by a certain formula that involves the central charges. Now, there's a computation I'm not really going to do before your eyes, but it's a definite computation. We have this moduli space of vacua, and it parameterizes everything, including the string coupling constant, or Newton's constant if you wish, and the radius of the extra dimensions and everything. So if you want to know how the theory behaves for strong coupling, that just means what happens when you go to infinity in G over K, or really in this double coset space. So we want to determine what happens when we go to infinity, and the way we'll determine what happens is we'll first use the supersymmetric formula to get the mass spectrum, and then we'll see how the mass spectrum behaves when you go to infinity.
An elementary question, but does the concept of the double coset space make sense mathematically?
Yes. It's not a homogeneous space. A double coset means that you divide on the right by something, and you divide on the left by something else. And actually, the kind of double coset space that appears here, where you divide on the right by a maximal compact subgroup and on the left by an integral form, is one that the number theorists are very fond of. I can't claim to shed very much light on why, but that's a fact of life.
That doesn't exist in all formulating like the standard coset spaces?
Well, I don't know what properties you want it to have, but I'll just mention one example. If you take SL2R, this is an example that comes in for some theories in some dimensions. The maximal compact subgroup is SO2, or U1, and the integral form is SL2Z. And then that double coset space is the moduli space of Riemann surfaces of genus 1. Because SL2R mod SO2 is the upper half plane, and dividing by SL2Z gives us the usual fundamental domain. So these things are generalizations of the moduli space of genus 1 curves. So, well, see, so even if we were in a single coset space, G mod K, going to infinity would just mean going to infinity in G. In other words, you could take a fixed point, maybe P in there, and take P going to GP. And G depends on a parameter T, and we want to take GT to infinity. And you can always assume you're going to infinity in a direction that looks like this, just using the real torus, well, using a diagonal matrix. Well, a couple of bits of things you have to show to argue that, but I don't want to go into that degree of detail here. And then if you go to infinity in such a direction, you can use the supersymmetric mass formula to determine the mass of a particle of type ij. Remember, there are 10 gauge charges, and for each gauge charge we can imagine a particle that carries just one gauge charge. I'll call that particle psi ij. And then the mass formula shows that the mass of psi ij behaves like this as we go to infinity. Well, what's it we really want to do? We want to know what happens for strong coupling. But, you see, strong coupling can mean different things. You can take Newton's constant to infinity, but you might be able to do other things that enable something peculiar to happen. So what we want to do in general is to go to infinity in all possible directions, including the direction where Newton's constant goes to infinity. We want to let all the peculiar coupling constants go to infinity and figure out what happens in any limit. So, by what happens, I mean I want to determine the low energy, the long distance effective theory when the coupling is big, when some of the couplings are big. And so, the long distance effective theory generically has only the massless particles we know about. But in some limits, extra light particles might appear. So we want to find all limits in which extra massless particles appear, except that we're really only interested in the maximal degenerations for as many massless particles that get light as possible. So you could have a limit where particles A and B become massless, and then if you perturb it by a relevant operator, you could give B a mass. So the basic case is to let E and B be massless together. You can always turn on some small perturbation that gives a mass to one of them. So what's really fundamental is to go to infinity in such a way that as many particles as possible become massless, and that gives the most complicated answers, and then those answers have relevant perturbations that give masses to some of the particles. I'm saying this too quickly, and I haven't justified everything I've said, but it turns out that way. So if you pose it that way, you find that there are two directions of going to infinity where as many massless particles as possible emerge. One of them is this, and corresponds to weakly coupled string theory, and the other one is this, and corresponds to 11-dimensional supergravity. When I say it corresponds to it, what I mean is that of the 10 types of particles, 6 are light in this limit, which is the correct number for the string theory if you think it through, and 4 are light in this limit. And 4 is the correct number for 11-dimensional supergravity, toroidally compactified to 7 dimensions. Because there are then 4 circles and 4 types of Kaluza-Klein winding modes that get light when the torus becomes big. So, in each limit, I won't work through details either of what I've said or of what I haven't said, but you find that in each limit, you get the spectrum which is expected plus the symmetries which are expected. And in particular, in the case of 11-dimensional supergravity, you see we were on 10 dimensions, and we toroidally compactified to 7. So, sort of 3 light particles are obvious, but the 4th appears when Newton's constant goes to infinity, and you get a symmetry between those 4. And that's a symmetry between the 11th dimension and the 3 that you had compactified in going to 7. So, in each case, you get the symmetries you expect, including traces of 11-dimensional Lorentz invariance in the case of 11-dimensional supergravity. Well, I haven't given a proper account of this, and I can't. Well, I could give a somewhat more proper account if I skip the second half of my talk. But to summarize it overall, what happens is that if you assume the duality symmetries that string theory has been suspected to have, then you can analyze all the strong coupling limits, the limit where Newton's constant or anything else goes to infinity, and you completely determine all the strong coupling limits, and you find that everything is either equivalent to weak coupling again, or it goes over to 11-dimensional supergravity with a big torus where the effective coupling is weak. So you get an effective determination of the behavior in all possible limits, and you see 11-dimensional supergravity with the symmetry between the 11th dimension and some of the others. So, to my thinking, it significantly strengthens the case for these U-duality symmetries and for the role of 11-dimensional supergravity. The summary of type 2 dynamics then is that type 2 dynamics is almost completely controlled by duality, with the only surprise being the role of 11-dimensional supergravity. So I've told you now, see, there are sort of 6 theories. There are the 5 string theories and 11-dimensional supergravity, and so far we've linked up 3 of them. 2 type 2 theories and 11-dimensional supergravity, and then the 2 heterotic theories were linked up with each other essentially by Narain. And the type 1 theory was linked up with type 2 by Dye, Fischler, and Polchinski. So the most fundamental question that's left is whether the heterotic string is somehow connected with type 2, which is what we'll get to in the latter part of the talk. That makes this much more interesting, because of course the heterotic string is the theory which for weak coupling, one that has uncanny success for weak coupling in giving the right qualitative structure of particle physics with the simplest assumptions.
And how far is now 11-dimensional supergravity here and supergravity theory? Is more a symmetry of the spectrum? So
No, it's...
Is it more?
Well, it has to be more because that's the only... The low energy interactions of that spectrum for unitary theory with supersymmetry are 11-dimensional supergravity.
On the other hand, as a fundamental theory, it's not completely safe.
As a fundamental theory, it's not completely safe. But now the question arises, let's go back to 10 dimensions. So, let's give an analogy though. We had 10 dimensions, let's consider two theories, QCD and 10-dimensional type 2A. Here we take Newton's constant to infinity. And here we don't have to take anything to infinity, we just go to big distances. Because the coupling constant gets big all by itself at big distances. In each case, the fundamental issue we really need to understand, the pressing issue, is to understand what's the long-distance physics. So the answer in the case of QCD is given by pi's, rhos, and nucleons. Now, is that a sensible microscopic theory? No, as far as we know. And it needn't be. It's the answer to this question, what's the physics of QCD? But it's not a fundamental sensible theory in its own right. It may be, however, that in the large n limit this becomes a fundamental sensible theory. That's an old conjecture whose truth we still don't know. But it doesn't have to be true. This is a perfectly good theory if all it is the answer to the question, what's the physics of QCD? In a similar spirit, we ask, what's the physics of type 2A in the limit when Newton's constant goes to infinity? And my answer is 11-dimensional supergravity on R10 times S1, where the radius of the S1 is Newton's constant to the 1/3. I called it lambda to the 2/3 before, but that's the same as Newton's constant to the 1/3. So that's an effective answer. If Newton's constant is big, you just work on this theory. And this theory is weakly coupled because the radius is big. The supergravity is a good description. But there's a question that I haven't addressed, which is one of the most fundamental mysteries here. In the limit where you actually is there actually a limit where you take Newton's constant to infinity, not just very big? When Newton's constant goes to infinity, this would have to go over to R11. And the question is there a consistent theory on R11, which is the strong coupling limit in 10 dimensions where Newton's constant is now actually infinity in the 10-dimensional sense? I know of no evidence for or against that. Of course, I mean, there definitely are people, for instance, people like Townsend, Bars, and others who have worked on supermembrane theory, who would try to give heuristic arguments for its existence. But to my thinking, there's no significant evidence for or against the existence of that 11-dimensional theory. Well, I'd have bet against it in the past, but I think we're now getting close enough that I'd no longer bet against it. I've become an agnostic. I think it's a fascinating question.
What's the dimensionless constant that you take to infinity?
It wouldn't have, what?
What is the dimensionless constant that you take to infinity?
Newton's constant in units of alpha prime. The string coupling constant.
But what is alpha prime percent?
No, this discussion is carried out in the context of a theory that makes sense. The theory that makes sense is the superstring in 10 dimensions. It has alpha prime and Newton's constant. Newton's constant is dimensionless in units of alpha prime. We've taken Newton's constant to infinity, and therefore we've lost a parameter. The one parameter that we had we set to infinity. So now we have a theory with no dimensionless parameters. I don't know if that theory exists, because I don't know if the limit when Newton's constant went. We determined the behavior when Newton's constant... See, what we determined was the behavior when Newton's constant is very big, like 10 to the 1,000. Then we determined the behavior at long distances. And we got interesting non-trivial behavior, and we could stop there. As Newton's constant gets bigger, the distances at which that description is good get bigger and bigger. So what I've said so far doesn't guarantee anything about the existence of a limit where Newton's constant is actually infinity. But nevertheless, that limit may exist. If that limit exists, the limiting theory is a theory in 11 dimensions. It'll be a supersymmetric, relativistic theory in 11 dimensions, with 11-dimensional supergravity as its low energy limit, and depending on no dimensionless parameters. Does it exist? I haven't the faintest idea. All I'm saying is that while in the past I would have bet against it, I shall place no such bet today. Yes?
Normally when you write the Einstein-Hill reaction for gravity,
Yes.
you don't specify what the topology of the space is.
Right.
So how is it that Newton's constant suddenly has something to do with the geometrical space?
Huh? Sorry. I can go through it again, but I only am discussing theories that are known to make sense. So we started on R10, but it could have been any 10 manifold. and a circle appeared out of thin air.
Yeah, in other directions.
If you start in 11 dimensions?
Right.
We can't start in 11 dimensions because we don't have a consistent theory. If you discover...
11-dimensional super.
But it doesn't make sense as a quantum theory. Or we presume it doesn't. If you discover the 11-dimensional theory that makes sense, then you can carry out your discussion.
Now let's talk about it as an effective theory. Just right in the
Okay.
branch, which apparently is
Okay.
supposed to be 11-dimensional.
Okay.
So,
Fine.
then what does this statement mean that
Well, I said that that effective theory might be the low energy limit of a theory that makes sense. I only said it might be. In the past I doubted it, today I'm an agnostic.
But what did you bring to the idea that it was membranes that might be that used?
Well, I don't see any evidence for that, which is why I didn't mention it.
But what argument is there?
What argument is there? Well, there is something fascinating here, which is that 11-dimensional, just as 10-dimensional supergravity can be coupled to a string world sheet, 11-dimensional supergravity can be coupled to a membrane. That's a very non-trivial statement because, well, it's really a miracle that was discovered by Townsend and others. I'm sorry I can't give the right reference now. That you can preserve what's called the kappa symmetry in the coupling of the membrane to 11-dimensional supergravity.
So that is the choice between membranes and
So,
strings.
it's a beautiful fact.
Yeah.
And there are those who believe it's a hint. There are those who have believed for years that it was a hint that the 11-dimensional theory existed. And there were people like me who considered the hint unconvincing. I am merely no longer willing to say I consider the hint
You
unconvincing.
have two choices.
Yes?
String or membrane. And you say, well, 50% chance membrane. That's
No, I know that this theory, I've told you something definite. There's a theory that really exists in 10 dimensions, and its strong coupling limit has a close relation to 11 dimensions. What I don't know is whether there actually is a limit as Newton's constant goes to infinity. If that limit exists, it would be the membrane theory people have wanted to talk about. So, I don't know. I'm just an agnostic on whether the limit exists, but I only said at the beginning of my talk that we were going to relate the 6 interesting known theories, 5 string theories and 11-dimensional supergravity. Well, there would still be 6 because supergravity would be a corollary of the membrane theory if it exists. One would reformulate my statement of the 5 string theories and 11-dimensional supergravity as the 5 string theories and membrane theory if you think the membrane theory exists.
it's an informal seminar, so in that sense it might be good to mention.
Well, if this is an informal seminar, I wouldn't have bothered wearing a suit. But anyway, feel free to go ahead, Peter.
I don't wear a suit, but it might be good for people to point out that the membrane is a generalization of string theory,
Yes.
but it has problems. First, it's non-renormalizable.
Yes.
String theory is renormalizable, and therefore people don't even know how to start the
Yes.
conversation. So what you allude
Yes.
to is an enormous new program. If you
That's right. Well, I don't think it's a program that will be solved that way. If it's correct, I do believe if it's correct, humans will eventually do it. But I think they'll do it in a completely different way.
Yeah.
The reason I think so is that the string theory had a coupling constant, but we took it to infinity, so we don't have a coupling constant anymore. Now we have a theory with no free parameter, so it won't have a Feynman expansion, and membranes won't... See, membranes aren't any good, as membrane theorists implicitly know, although they don't like to put it that way, because papers on membranes failed to make sense out of quantum membranes. What the membrane theorists could have strengthened their case if they had said not merely that membranes aren't any good, but membranes shouldn't be any good, because there isn't a dimensionless coupling constant in the theory that they're trying to describe. So, membranes aren't and shouldn't be any good, and therefore the question is there some other reason you can discover that that theory should exist? Good question, I don't know. All I can safely say about it is that it would be pretty interesting to know about it. Well, I have the choice of talking twice as fast or not finishing in time because of all the questions. Or of course I could lop out half of the rest. I'll try to make a compromise.
We're getting extended time.
Well, I appreciate your remark, but I didn't hear a unanimous vote by the audience.
This is actually a custom that the speaker begins and then it goes longer.
Okay.
So please.
Well, I wouldn't want to break your customs here.
Already did with your suit. Okay, but whatever you like.
Okay. Well, as I said, if we want to learn that the 6 theories are different manifestations of the same thing, the fundamental thing we need to do is to bring in the heterotic string. So we'll try to learn something about heterotic string dynamics. But now, instead of 10 dimensions, we'll start in 5 dimensions. The reason I started in 5 dimensions, in part, was that when I was originally doing this, I was aiming for something quite different. I was hoping to prove that the theory didn't make sense in 5 dimensions, thus explaining why we lived in 4. But that didn't happen. It turned out it made sense in a way that draws upon those duality symmetries and gave me a lot more confidence in them. Anyway, we'll start in 5 dimensions. And what's special to 5 dimensions is that in 5 dimensions, the 2 form B of the supergravity multiplet is dual to a vector, which I'll call C. That's only true in 5 dimensions, that dB and dC are a 3 form and a 2 form, which are dual. Now, C doesn't couple to charged elementary string states. It hardly could, as it only exists as a vector in 5 dimensions, while the elementary string spectrum can be continued out of 5. But it's easy to find charged particles that couple to C. This is different from the first case I gave you. We have the same puzzle, a U1 gauge boson, for which it doesn't couple to elementary string states, and we wonder what it couples to. But while in the other case we needed to speculate about extreme black holes, or at least charged black holes, here there's a definite answer that I can just give. An answer that's definitely true. So we've got the equation that's related to anomaly cancellation for the field strength H of the 2 form, but in terms of C, that tells us that the dual of the instanton density is the electric charge density for the dual vector. So we learned that instantons, good old Yang-Mills instantons, good old 4-dimensional Yang-Mills instantons that we usually use for other purposes, are electrically charged particles in 5 dimensions for this theory. And therefore we know the mass of an electric charge. The mass of the electric charge is the action of the Yang-Mills instanton, 16 pi squared over lambda squared, times the absolute value of the instanton number, which is the electric charge. Now, just as in our other case, it's very, very plausible that that formula is exact because of the self-duality of the classical instanton solution, which causes the multiplet to be small, and the supersymmetric analysis strongly suggests that the formula is exact. And if we accept that the formula is exact, we can try to follow it into strong coupling just as we did before. Now, there are a couple differences. One is that we're discussing a particle that we know about definitely, related to Yang-Mills instantons, whereas in the other case we needed black holes. And the other is that we have a 1 over lambda squared, which is the conventional behavior of a soliton, whereas the other case had an unusual 1 over lambda. But otherwise, we follow in the formula to strong coupling. So we try to follow it into strong coupling where these states become very light. And just as in QCD, or in our previous discussion, we want to determine what are the light states for strong coupling, and we want a reasonable description of their dynamics. Reasonable means an effective, useful description. A description that will be weakly coupled. We want to find a description that you can really use to effectively calculate the properties. If you had an accelerator that could produce the light particles, we want to be able to actually predict their behavior. Well, from our previous experience, we know what to try. Namely, we've got this infinite set of multiplets. They're rather nasty things. Now they are massless charged spin 1 particles. Light charged spin 1 particles for large lambda, infinitely many of them. But we know what to try to do. We interpret it in terms of Kaluza-Klein modes on a circle. So we conjecture that the strong coupling limit on 5 dimensions shall involve some kind of a theory on R5 times a circle, where the circle grows when the coupling goes to infinity. But we seem to be in trouble, because what is this circle? That circle would appear to be an 11th dimension, just as in the other case. And that was fine for type 2, because 11-dimensional supergravity, which had the right spectrum, came galloping in from the horizon. But how can the heterotic string possibly be derived from an 11-dimensional theory? Now, it's true that there were 5 other dimensions hanging around, so you could think of trying to use one of them. Let one of them grow like this and leave the other 4 dangling in thin air. The trouble with that is that the 5 compactified dimensions that were already there carry some symmetries. For instance, the T-Duality symmetries of the compactified string theory. And none of them is a singlet under those symmetries. And here we need to pull out one of the 5 dimensions that would have to become a singlet, leaving the 5-dimensional T-Duality symmetries to be carried by 4 dimensions, which sounds impossible. But luckily, these questions have a nice answer. In fact, there's an already conjectured relation of the heterotic string to type 2, which is the proposal that the heterotic string on R6 times the 4 torus is the same as type 2a on R6 times the K3 surface. The conjecture was originally based on the fact that the 2 theories have the same supersymmetry and the same moduli space of vacua. A Sabin, which locally is due to Narain for the heterotic string and Seiberg for type 2. And globally it's due to Aspinwall and Morrison for type 2. But I'll give some additional arguments for this conjecture. First argument is the first argument we had in the other case. It's true that the 2 theories are equivalent at low energies, but if you work out the precise equivalence, you see that this equivalence maps weak coupling of one to strong coupling of the other. That's a necessary condition, because it's certainly not the case that weak coupling of one theory is equivalent to weak coupling of the other. If this particular point came out the other way, we could say that this conjecture was false. Point 2 is that this conjecture will cure our puzzle in 5 dimensions. And point 3 is that it implies S-duality in 4 dimensions. So all the evidence for S-duality developed in the last 4 years. S-duality is a cousin of the stuff I was talking about yesterday in my informal talk. All the evidence, the fact that S-duality is a corollary of this is a strong hint that this should be, since S-duality seems to be true, is a strong hint that this seems to be true. And then, well, there's an interesting point that the points in moduli space where the heterotic string gets an extra gauge symmetry have the ADE symmetry of one corresponds to an ADE singularity of the other. And then finally we'll get an attractive picture of the dynamics in 7 dimensions. The last point is that Sen, and especially Harvey and Strominger, showed in the last couple of weeks even that you can even realize the heterotic string as a soliton in the type 2 theory. Well, I'm really going to just be very sketchy and give a hint, because I'd like to come pretty close to finishing on time. Here I've written the 2 low-energy supergravities, and they look the same, except that for the heterotic string, e to the minus 2 phi multiplies everything, but for type 2 it doesn't multiply the Ramond-Ramond field strength. So it looks impossible for these to be equivalent, because they're totally the same except for one term. Yet they have to be equivalent because of the low-energy supergravity. Well, it turns out that they're equivalent, but they're equivalent by a highly non-trivial map. You see, if there was an e to the minus 2 phi multiplying this term, they'd be trivially equivalent, and therefore we could say that this conjecture was all bunk. It would map weak coupling to weak coupling, and it would be wrong. Luckily, one of the two theories is missing a term the other has, and therefore it takes some magic to make them equivalent even at low energies. And the magic involves exchanging weak and strong coupling, making a Weyl transformation, and making a duality transformation for the 2 form. This uses the fact that in 6 dimensions a 2 form is dual to a 2 form. Well, my first 3 points follow from the structure of this transformation. The first point, for instance, says that weak coupling of one is strong coupling of the other, and that's why we avoid an immediate contradiction, but that gives us the beauty. If the conjecture is true, it determines the strong coupling limit of either of these two theories in an effective fashion, it simply being the weak coupling limit of the other one. Then the Weyl transformation, or more precise use of those formulas, shows that if we now try to do the heterotic string in 5 dimensions, that means we take the 6 dimensions to be R5 times a circle, then our relation, and we want to keep the radius of the circle fixed while taking Newton's constant to infinity. Our relations say that although in the heterotic description the radius is being kept fixed, in the other description it's growing because of the Weyl transformation. And so the heterotic string in 5 dimensions with Newton's constant going to infinity becomes the other theory in 6 dimensions. So 5 dimensions does turn into 6 when Newton's constant goes to infinity. And if you ask, how can the symmetries of 5 dimensions be carried by the symmetries of the other 4 dimensions? That takes a little bit of magic and has to do with the mapping between the moduli spaces of the 2 different theories that was mentioned before. Well, I've essentially showed you, perhaps I zipped through it too fast, that the string-string duality in 6 dimensions determines what the heterotic string does for strong coupling in 6 dimensions and in 5. In 6 dimensions it turns into type 2, again in 6 dimensions. And in 5 dimensions it turns into type 2, but again in 6 dimensions. A slightly different type 2, a subtlety I didn't explain. I skipped some transparencies. Suppose we want to know what the heterotic string does in 4 dimensions. Well, when Newton's constant goes to infinity, the obvious thing is to take the 6th world to be R4 times 2 circles and try to use the string-string duality to map it onto type 2. If you do that, you get a true statement, but not a useful one. It's not useful because the effective coupling at the relevant length scale is big. Remember, what we want to get is to usefully determine the strong coupling limit in the sense of getting a weakly coupled description. Here we get a description that's again strongly coupled. But there's an amazing way, foreseen by Duff, of getting around this. And I think in view of the time, and also that it's explained in my paper, I won't now explain it properly, but I'll simply say that Duff observed the possibility for something which actually occurs in this theory, that if you take the heterotic string on R4 times the 2 torus, it has a symmetry we know about, which is T-Duality, and a symmetry we don't understand, which is S-Duality. And likewise, type 2 has a symmetry we know about and a symmetry which we're not sure of. But Duff pointed out a mechanism by which this string-string duality would turn the symmetry we understand into the symmetry we don't understand. And that mechanism is realized here. So this string-string duality in 6 dimensions implies S-duality for both theories in 4 dimensions. And therefore, I can tell you that if string-string duality is true in 6 dimensions, then in 4 dimensions, the strong coupling limit of the heterotic string is itself again. So I'm going too fast for you to really absorb this if you haven't looked at the paper. But what I've tried to convey is that the conjecture determines the strong coupling behavior of the heterotic string in 4, 5, or 6 dimensions, giving completely different answers in the 3 cases. Well, I have 2 more points I'll mention briefly. Well, the first one is a point I don't really understand. Subsequent work by Harvey and Strominger sheds a little bit of light on it, but I won't try to absorb that today in this talk. But one of the strange things, I'm just going to tell you an interesting fact, which is suggestive, but doesn't really explain the phenomenon. The heterotic string on R6 times the 4 torus, its most interesting property is no doubt that it gets enhanced gauge groups with an ADE classification at many special points in its moduli space. At precisely those points, the K3 in the equivalent type 2 theory can be shown, I explained this in my paper, to develop an isolated singularity with the same ADE classification. So this one is trying to imitate this one. And Strominger's last paper, well, the last 2 papers they wrote, even perhaps sheds light on the mechanism by which it happens. Well, there have been two parts of this talk. One got a little bit blue shifted, the last one, and the first one got a little bit red shifted. They were meant to be more nearly equal in length. But you may have noticed a certain disharmony between them. In the first part of the talk, we related a 10-dimensional theory to 11-dimensional supergravity. See, in the first part, we related type 2 to 11 dimensions, and in the second part, we related type 2 to the heterotic string. Well, if both statements are true, shouldn't 11-dimensional supergravity be more directly relevant to the heterotic string? In my last point, I'll propose a situation where that seems to be true. The strong coupling limit of the heterotic string in 7 dimensions seems to be 11-dimensional supergravity on R7 times K3. For instance, the 0th point here is that in each case the moduli space of vacua is the same, namely a double coset space. I wrote this as a single coset space, but you should divide by the integral form. You get a double coset space times the positive reals, where in one case the positive reals, well, in one case, for instance, this is the moduli space of classical K3s. In the other case, it's the T-Duality group. In one case, the R plus measures the string coupling constant. In the other case, it measures the volume of the K3. Moreover, a sine qua non of this proposal is that when you match up the 2 theories, you find that they match at low energies in such a way that strong coupling of one goes to large volume of the other, and weak coupling goes to small volume. So, the limit where one description is bad is the limit where the other description is good, avoiding an immediate contradiction and meaning that the relation is useful. The weak coupling limit of either one was already known, and the strong coupling limit of one is the weak coupling limit of the other. So, you can make this more precise as I did in my paper, but I won't do so now. Well, we've determined, I think, the strong coupling behavior of all the type 2 theories in any dimension, and of the heterotic string in 4, 5, 6, or 7 dimensions. And I think if we want to go below 4, that's essentially a corollary of what happens in 4. But you might still ask about what happens to the heterotic string in 8, 9, or 10 dimensions. That hasn't been answered. There's an old conjecture by Strominger, of which I'm no longer as skeptical as I was, which was that the strong coupling limit in 10 dimensions was some kind of 5-brane theory, whatever that is. And there's another peculiar proposal about this that I made at the end of my paper, but which doesn't have evidence comparable to the evidence for the things that I've explained to you. We may make the amusing remark that the SO32 superstring And the type 1, the SO32 heterotic string and the type 1 string in 10 dimensions have the same low energy behavior, same low energy limit. And once again, they have the same low energy limit by a transformation that exchanges weak and strong coupling. So we can ask whether the heterotic string of strong coupling in 10 dimensions with SO32 is simply type 1. And if that's true, the another way that type 1 comes in, independent of what Dai, Lee, and Polchinski did a few years ago. And if that's true, it would determine the behavior for both heterotic theories in 8 or 9 dimensions, leaving E8 times E8 in 10 dimensions as a mystery. Maybe that one has to be the 5 brane. Well, I hope to have convinced you. You see, our experience in 4 dimensions has been that if you get over your initial fear and jump into the water, as was pioneered especially by Natty Seiberg, you can actually determine the strong coupling limit of 4-dimensional supersymmetric field theories. I hope to have convinced you that we can do the same thing for string theories. Of course, some of it was already done with S-duality in 4 dimensions. I hope to have convinced you that in the process, we get much stronger evidence for some of the dualities, and that we learn something which I think is fundamental, that all the different string theories are really one. And we see, I think, for the first time, some of the completely new phenomena that occur when Newton's constant is big. Some of the new phenomena that we wondered about in past years or decades but didn't have examples of when quantum gravity is big. In string theory, quantum gravity makes sense. What does it do? Well, when it's weak, it doesn't do much. What does it do when it's strong? Well, it magically, among other things, it magically materializes new dimensions that weren't there. I'm sure it does many other things. I hope we'll learn some of them in the next few years. Thank you.
Are there any questions?
What would be involved in duality is so useful. It's a useful concept. What would be involved in demonstrating the status of it? I mean, just in a qualitative sense, how could one imagine this coming about?
I can't imagine it. I think we have to learn something fundamental new. And that's one of the things that makes it so interesting. The same is true even in 4-dimensional string theory, let alone field theory. We know by now that for n equals 2 QCD, duality is the key to the dynamics, as Seiberg and I showed. And Seiberg separately showed subsequently that for n equals 1 QCD, duality was the key to the dynamics. For a few months, people asked whether it was true for n equals 2 but not 1. And now for 7 months, we've been wondering whether it's true for n equals 1 but not 0. One of these days, we might learn that duality is also the key to the dynamics for n equals 0. In other words, for ordinary game states without any supersymmetry at all. And that will sharpen, as it happens, the puzzle of actually understanding these dualities, instead of just guessing them, determining their consequences, and exploiting them. I think we know that, at a physicist level of confidence, definitely know that these dualities are true. The evidence is overwhelming from so many different directions. And we know that their consequences are deep. For instance, they determine QCD dynamics, at least for n equals 1 and 2. They determine much about the geometry of form elements. They give us, as I said, our first indications of how quantum gravity behaves when it's strong. But we're far from understanding these dualities. And I think it's really hard to guess what the world would look like if we did.
You mentioned the equivalent of SO32 as 1 as what happens to the heterotic?
First, I want to say that the evidence for this is very slight at best. So I mentioned this, let's even call it a speculation. I made that speculation. And for E8 times E8 in 10 dimensions, I don't even have speculation. Although Strominger made what I call speculation about 5 things. That speculation didn't even have as much evidence in my opinion as this speculation has. Although opinions were different. Now below 10 dimensions, E8 times E8 and SO32 are equivalent. So in 9 and 8, they're equivalent. And therefore, either of these calculations are true is relevant to the three below 10 dimensions.
That's kind of funny because you assumed it was true in tiny dimensions also. And there's this anomaly thing about SO32 and type 1, and you can also have D8 plus D8 type 1.
No. I don't know what would happen. But we saw for type 2. Type 2A and 2B are equivalent below 10 dimensions. But in 10 dimensions, not only are they not equivalent, but their strong coupling limits are completely different. One of them has itself with a strong coupling limit, and the other one pops us in 11 dimensions. So now that's going to be the same thing. E8 times E8 and SO32 are equivalent below 10 dimensions, but in 10 dimensions, their strong coupling limits could be completely different.
And I'm confused about your picture. It's saying you only have one string, and then one string where you then have two.
With in the lowlands. And occasionally we climb over the low mountain passes. Or we climb over a low mountain pass, we learn something. And we've learned circuitous routes that take us over the low mountain passes, which enable us to map one theory to another. Up there in the sky, perhaps visible from orbit. Visible from orbit, you can answer his question with probably also yes.
You can classify a theory. It doesn't give you a new theory. It gives you new action.
Let me tell you, I'm going to state precisely my philosophy of these things. A given theory has many manifestations and factorizations. If I have two theories A and B, and I can see that one manifestation of A is equivalent to another manifestation of B, I declare that that means the theories A and B are equivalent, and that the other manifestations of A and the other manifestations of B are all manifestations of the same thing that I don't understand. That's my philosophy of determining the two theories are equivalent. In that sense, by climbing over some of the minor mountain passes, we've seen that the 5 theories plus one-dimensional supergravity are equivalent. And up there are the lofty peaks, and maybe have to get into orbit. And then all this presumably becomes obvious along with a lot of things. That's my philosophy.
Let's think